Right. Hi, folks. If you were here this morning, I'm sorry, you've got me again. If this is your first time hearing me, congratulations. You get to hear me talk. You didn't miss out this morning. So as with this morning, this is what I like to call a no man left behind lecture. If at any point you are lost or confused, that's my fault for getting you confused, not your fault for being confused. So please do feel free to ask clarifying questions throughout. So I'm going to be talking a little bit about Bayes today, but I wanted to start off with a very important bit of context that I feel is just critical to understand the rest of the presentation. And that's that I'm a massive nerd, huge nerd. I play a lot of board games. I play a lot of Dungeons and Dragons. As you can see from my online profile, I've logged over 800 hours on Dungeons and Dragons. Don't tell my supervisor. And as such, I have a strong love-hate relationship with dice. In particular, at the moment, there's a dice that I'm pretty sure is trying to kill me. And I'm not alone. There are a lot of people within the board game sphere that have strong opinions on dice. This is a dice jail. There are dice thrones, dice dunce chairs. There are entire websites dedicated to how to correctly train your dice. But I decided I'm a scientist. I don't need to rely on all of this. I will use science to help decide whether this dice really is trying to mess with me or not. So I took a 6-sided dice and I rolled it 200 times, and then I wrote out all of the results, which you can see here. And obviously the question that I now really want to ask, my hypothesis is that this is a biased dice. So what I really want to know is, given all of that data that I've just accumulated, given all of those rolls of the dice that I've just made, what is the probability, what is the likelihood, what is the chance that my dice really is biased against me? And this is where we come across Bayes for the first time. If you haven't come across Bayes since primary school days or before, do not worry. You may remember it looking something a little bit like this. Bayes is all about probabilities, specifically conditional probabilities, probabilities of causes. What is the likelihood, the chance of A given B? What is the probability that my dice is biased, given all those dice rolls I've just made? What is the likelihood of finding a fork in the CBU kitchen if I'm trying to have lunch after 1 p.m? It's 0, by the way. What is the likelihood that there is a fire if I can smell smoke? What is the probability that my hypothesis is true, given the data that I observe? And if you're not a big old statistician, you might not have realized that this isn't actually what you're doing when you're using traditional frequentist statistics, things like p-values. This isn't actually the calculation that we're calculating. See, what we're actually asking with p-values is a little bit closer to this. Instead of asking what is the probability of my hypothesis given my data, you're instead asking what is the chance that I get this data that I observe, given that my null hypothesis is true. So what is the probability that I get this data, or more extreme data than this, in a world where my null hypothesis is true? What is the probability that I rolled these rolls, or something more extreme than this, in a world where my dice is actually fair? And this is where our magical p is less than 0.05 comes in. Because when we're using our magical p equals less than 0.05, what we're actually saying is that there's a less than a 5% chance that these data would arise if the null hypothesis that our dice is fair is true. So in this case, if I rolled all my dice and I did our analysis, my p is less than 0.05, there is a greater than 95% chance that my dice rolls arise from a world where my dice is biased and actually trying to kill me, and I therefore might decide that my dice does in fact deserve to go into dice jail. And if you've been listening to this, you might start to feel a little bit confused. Trying to kind of get your head around what a p-value is actually calculating, what it's actually doing down at the nuts and bolts of it, isn't a particularly intuitive process. The likelihood of our data or something more extreme given the null hypothesis isn't really what our brain intuitively wants to do. In fact, it might be one of the least intuitive ways I can think of getting around it. And so your next response might be, well, why should I care? Okay, so down at the nuts and bolts of it, it's a little bit counterintuitive. Who really cares? It's a standard convention. We've been using it for decades. It's appeal to authority. I know everyone that uses p-values. Why should I care if when I get down to the nuts and bolts of it, it isn't maybe quite the most intuitive thing in the world? And I would argue that the reason that you should care is precisely because it's not intuitive. And when we're using something that is unintuitive to get our results, what that can lead to is us making inferences that aren't actually supported by the statistics that we're reporting. So when we make statements like, I accept the alternative hypothesis, or I have more evidence for X than Y, something is more significant than something else, we actually have to be really wary about the language that we're using, because some of these statements don't actually logically and mathematically follow on from the frequentist statistics that we're using. And I think, are gradually learning to be a lot more cautious about how we interpret p-values. There's a bit of a crisis of confidence, particularly coming about because of the replication crisis that happened across psychology and neuroscience a little while ago. So I think for me, reason number one that you should care is precisely because it's not necessarily the most intuitive thing in the world. And I think when we have to focus very hard to make sure that our interpretation of results is valid based on the statistics that we're doing, it just leaves us open to making inferences that we can't actually make. The second reason is our magical p is less than 0.05. This is a bit of an arbitrary cutoff, and I think this is something that we've just kind of all accepted. We have to have some kind of cutoff for significance, because significance is actually binary. Something is either significant or it's not significant, and we had to pick a value, and this is the one we go with. And whenever I teach A-level psychology students about why we chose this value, the standard line is that it's a good trade-off between a type 1 and a type 2 error, between a false positive and a false negative. And while that is true, the answer is also just a little bit, we kind of had to pick a number. That's the number we chose. We put a little halo on it. I added wings to make it look a bit nicer. So it's a bit arbitrary, and that can have a negative influence, because what happens when we have this? When we have this, the level of inference that we can make really drops, because now we don't have a significant result. What can we say? If you had a result of p equals 0.06, would you honestly say you accept the null hypothesis when you expected there to be an effect there? Would you carry on collecting data? Something you really shouldn't be doing, but a lot of people do. You can't say that you have, you can't say that there's nothing there. You might say that, well, maybe I'm just underpowered, but you really can't tell the difference. And because of this lack of inference that we can make when we have a non-significant result, we start to get even more motivated to have a significant result, because we can just say so much more about it. And so I'm not saying that any type of statistics is immune to bad science. Of course it's not. But I think having these arbitrary cutoffs where there's such a big difference in the level of inference we can make really does encourage some bad scientific practices like p-hacking. So, despite the name null hypothesis testing, we kind of do get left in the lurch a bit with these kind of statistics, because in the words of some mathematicians, null hypothesis testing, despite the name, has a violent bias against the null hypothesis itself, against confirming it versus just saying we're underpowered. So hopefully at this stage, I've got you at least somewhat convinced that there might be a few issues with frequentist statistics. And these are probably issues that you're already aware of in some shape or form. And the now question becomes, what's the alternative? There are lots of alternatives to traditional frequentist statistics, not only swapping out p-values, but adding things in. Things like confidence intervals can be fantastic, calculating effect sizes can be a great way forward, but it may be completely unsurprising, given the title of this talk, that I'm going to hone in particularly about Bayes. And my hot take, that I'm very happy to discuss afterwards, is that if we had the computational power that we have today, p-values would never have had a look-in. Because years and years ago, many decades ago, when p-values weren't the common practice, there was a big debate around whether we should be using frequentist statistics like the ones we use now, or Bayesian methods. And ultimately, one of the big factors of why frequentist statistics won out was that it was easier to calculate at the time. It was kind of a bit of a shortcut. And now that we have the computational power to be able to do Bayes almost as easily as our frequentist methods, we're really seeing a reignition of this debate about which type of statistics we can use. And Bayes factors are helpful because they really are calculating this. Going right back to the beginning, they're calculating the probability of a hypothesis given the data we observe, not that kind of a little bit strange inverse that we see in frequentist statistics. What is the probability that my hypothesis is true given the data that I see? Another advantage is that even though Bayes does still suffer from some arbitrary cutoffs, there are kind of established conventions of how to interpret, in this case, a Bayes factor, BF, rather than a p-value. This is kind of your summary statistic. Traditionally, a Bayes factor of 3 is moderate evidence for the alternative hypothesis. So this is kind of the closest we get to an equivalent of p is less than 0.05, where we'd be confident saying, yeah, there's something going on here. But the advantage of Bayes factors is you really can interpret them as a continuum. And this is a continuum which goes towards the alternative and also towards the null. there isn't the same violent bias in Bayesian statistics that we see in frequentist statistics, because when you accumulate evidence, you accumulate it both ways. Now, in this case, a Bayes factor of 1 basically says we don't have evidence either way here. You don't have evidence for your alternative hypothesis, you don't have evidence for your null hypothesis, you might want to collect some more data. But if I have a Bayes factor, say, over 3 in this case, that represents moderate evidence towards my alternative, that goes out towards infinity, getting stronger and stronger evidence. But if I start going the other way, if I get to under a third, then I start reaching moderate evidence for my null hypothesis. I'm not underpowered, I'm powered. It's just I'm powered and there's no effect. Allows that extra level of inference. And this means we really can make statements like this. There is stronger evidence for the alternative, there's moderate evidence for the null. It also gives us much more flexibility because we can interpret them on a continuum, though we do have those arbitrary thresholds that a lot of people use. We might be more lenient when we're dealing with small patient groups, for example, that are difficult to collect. Or we might be more stringent, asking for higher levels of evidence when someone's replicating what should be a very well-established effect. We also don't have to worry quite as much about things like post hoc tests or multiple comparisons. There's a bit more of an asterisk next to that one, depending on which mathematician you ask. So the next question then is, if Bayes is so great, if it can maybe solve some of the problems that we have with age-old statistics, how can I implement this? And the answer is, quite easily. Hooray! Like I said, the computational problems of yesteryear are not computational problems we have today. So if you would like to use Bayes factors alongside or instead of your traditional p-values, you can implement them in all of your favorite packages. RStudio has a Bayes factor library that you can literally use t-test bf instead of t-test to run exactly the same t-test, but using with a Bayesian output. There are also packages in MATLAB, and if you would rather use a GUI, something more akin to SPSS, but better, even if you don't want to use Bayes, use JASP. It's free to download, and you can run frequentist and Bayesian statistics in JASP. And if that isn't enough to convince you, you can save your figures as PowerPoint files and edit them in PowerPoint. You're welcome. It's beautiful. So if you're just looking to add those onto your traditional analyses, all of your classic tests, ANOVAs, principal components analysis, t-test correlations, you can absolutely do that. But Bayes also allows us to go a little bit further. So other Bayesian analysis techniques that we might have come across are things like Bayesian hierarchical modeling or dynamic causal modeling from this morning. And even though these are categorically very, very different approaches, Bayesian hierarchical modeling can be used for a range of data, from behavioral data, epidemiological data, whereas dynamic causal modeling is based on functional imaging data. They use vastly different inputs, outputs, methods, but there are some commonalities in their Bayesianness that comes with a lot of different Bayesian modeling techniques. The first is the inclusion of priors. These are prior expectations that we can build into the model. This is also a criticism we see leveled at Bayes sometimes, which is a fair one, is that when our results are dependent on the priors that we put in, that can make people a little bit cagey. To that I'd say that's what we do in science. Every time we ask a question, we're going in with our prior beliefs. We ask specific questions because of beliefs that we've generated from the literature. So to me, it's kind of putting that into the statistics as well. Different priors depending on literature, depending on different levels of the model in the case of Bayesian hierarchical modeling. They also can model uncertainty, which can be really helpful, good at dealing with uncertainty in our data and in our output. And they're also primed for model comparison. Bayes is really this hypothesis testing machine where we're comparing hypotheses off against each other, which can be really helpful. But even going beyond analyses, Bayesian techniques can help us with things like data collection. As I said, when we don't have to worry about multiple comparisons, we can use something called Bayesian sequential hypothesis testing. And this means that instead of stopping when we reach p equals 0.06 and being unable to carry on, because that's just mathematically not good behavior, it's not good science, with Bayes we absolutely can. Because we're not increasing our chances of a false positive, we're accumulating evidence in either direction. So when we reach this very sad number, what we can instead do is say our Bayes factor shows we don't have evidence for either way, let's carry on going. And that's a technique that I've used in my own research, and just an extra incentive to try and make sure that we're powered. I think it's summarised quite nicely in this paper that I'd recommend by Deans. Having tested once at the 5% level, an experiment yields a p of 0.06. One cannot reject the null on that number of subjects, yet one cannot accept it either. No matter what the official rules are, would you accept the null for a p of 0.06 when you have predicted an effect? One cannot publish the data, yet one cannot in good heart bin the data and waste public resources. That would be immoral. And it is a quandary that we're stuck in with frequentist statistics when we reach that level. Whereas with Bayesian sequential hypothesis testing, we can keep adding participants to make sure that our study is powered and that's statistically a valid move. Outside of the realms of methods, we can also use Bayesian approaches to generate new theories. The Bayesian brain, for example, is a theory in which we say that the brain is a model-making machine, iteratively generating new models of its environment by combining prior expectations of the world with sensory observations of reality. For example, if it's your birthday, you might expect presents, cake and candles, but you walk downstairs to find nothing, and therefore you must update your belief, perhaps reflecting the fact that you're too old now to expect all those things on your birthday. And this has been used to describe a vast array of symptoms, including hallucinations in schizophrenia, tics in Tourette's, hysteria, and in my own research, looking at some new approaches to apathy and impulsivity in dementia. With that, I'm very happy to take any questions you have, or if you'd like to try and implement Bayes in your own research, feel free to give me an email. Thank you.